Hello everyone, welcome to my YouTube channel Olympiad Geometry. In this channel, we will talk about the plane geometry, solid geometry, and analytic geometry in Math Olympiad computation. We will start from the plane geometry and mainly focus on it. We will learn most popularly used theorems and methodologies in solving geometry problems. Then we will look at math computation problems in each year. The video will be made in Chinese and English version. This is our first video of the English version. Let's start with the Menelaus theorem. The Menelaus theorem is saying, let me draw the figure first. It's saying, let ABC be a triangle. Let DEF be points on BC, CA, and AB, or their extension respectively. If points DEF are collinear, then AF divided by FB times BD divided by DC times CE divided by EA equals to 1. So let's prove this. The first thing we need to notice is that how we can write this equation. Right, it starts from the, we look at the ratio of AF divided by FB. They're all on the same side. It starts from a vertex and stop at the intersection point. That's the numerator, AF. And for the denominator, it starts from the intersection point, F, and stop at the vertex B. And for the second term, it starts from the vertex B, which is the same point of previous term denominator vertex, and stop at the intersection point, right? So that's BD. And divided by DC, so the denominator is still start from the intersection point and stop at the vertex. So similarly, it start from vertex C, stop at the intersection point E, and start from intersection point E, stop at the vertex A. Right? That's how this equation is written. So we want to find the relationship between AF and FB, or the relationship between BD and DC. We notice that for the BD and DC, we can transfer it to the side AB. Right? How do we transfer the ratio BD divided by DC to the AB side? We can do a line through point C that in parallel with FE and intersect with AB at H. Right, so we get CH in parallel with FD. That means in the triangle BDF, because CH in parallel with FD, so BD divided by DC, BD divided by DC equals to BF divided by FH. Also in the triangle AHC, because HC is in parallel with FE, so CE divided by EA, that's this term, CE divided by EA, equals to HF divided by FA. So we can replace term BD divided by DC by the term BF divided by FH, and the term C divided by EA to the term HF divided by FA. So it becomes to AF divided by FB times BF divided by FH times HF divided by FA. So we know that AF equals to FA, HF equals to FH, BF equals to FB. So this production is 1. That means AF divided by FB times BD divided by DC times C divided by EA equals to 1. So we prove the Menelaus theorem. Now we look at the converse of Menelaus theorem. It seems that let ABC be a triangle, let DEF be points on BC, CA. Let me draw the right. So let DEF be points on BC, CA, and AB or their extension respectively. If AF divided by FB times BD divided by DC times CE divided by EA equals to 1, points DEF are collinear. Here I want to introduce a methodology that widely used in geometry problems. It's called proof by contradiction. It seems that something that leads to a contradiction cannot be true. And if so, the opposite must be true. Let me repeat it again. Something that leads to a contradiction cannot be true. And if so, the opposite must be true. So for this problem, we want to prove that points DEF are collinear. We want to prove this one. So let's assume DEF are not collinear, right? DEF are not collinear, but this equation is a condition that we already know it's true, right? So AF divided by FB times BD divided by DC times CE divided by EA equals to 1. But we assume that DEF are not collinear. So if we extend FE that intersect with the extension of BC, we can call this point as D prime, right? And we know that D is on the BC. It's just a different point with D prime. So D and D prime are different points. So we can use Menelaus theorem on triangle ABC and line FED prime, right? Because FED prime are on the same line. They are collinear. So we can do this. That means AF divided by FB times BD prime divided by D prime C times CE divided by EA equals to 1. This is valid because of the Menelaus theorem. And this is valid because of the condition, right? We know this condition is true. That means BD prime divided by D prime C equals to BD divided by DC. Right, so BD prime divided by D prime C equals to BD divided by DC. So let's do a trick here. BD prime divided by D prime C minus 1 equals to BD divided by DC minus 1. That means BD prime minus D prime C divided by d prime c, right? bd prime minus d prime c, bd prime minus d prime c, that's bc. So bc divided by prime c should be equals to bd divided bd minus dc, that's bc, divided by dc. This is true because bc equals to bc, so d prime c equals to dc. That means d prime and d are the same point, which we see, so d prime and d are the same points, right? This conclusion contradicts with the conclusion that d and d prime are different points, which means our assumption is wrong, right? Our assumption is wrong, which means the opposite of the assumption is correct, right? It's true. So the opposite of the assumption is that D, E, F are collinear. So we prove the converse of the Menelaus theorem. Now let's see the Menelaus theorem in angle form. Let me draw the figure first. Let ABC be a triangle. Let DEF be points on BC, CA, AB, and all the extensions respectively. Points DEF are collinear if and only if sine angle BAD divided by sine angle DAC times sine angle CBE divided by sine angle EBA times sine angle ACF divided by sine angle FCB equals to 1. Again, let's observe this equation and understand how these angles are written, right? BAD, right? On the numerator is BAD. So that start from our text and go to the next vertex, that's BA, and then go to the intersection point, that's D, right? That's on the numerator. And on the denominator, it starts from the same intersection point and go back to the, look at this, go back to the vertex and then go to the next vertex, that's C, right? So for the numerator, it starts from one vertex, go to the next vertex, and then the intersection point. And for the denominator, it starts from the same intersection point, go back to the vertex, and go to the next vertex, right? So again, for the numerator, it starts from the vertex used by the denominator in previous term, and then go to the next vertex and go to the intersection point. And for the denominator, that from the intersection point go back to the right, same vertex, go back to the same vertex and then go to the next vertex. Similar thing here. So vertex, intersection point, go back to the vertex and then go to the next vertex. So because let's do this, we assume DEF are collinear, right? So we want to prove this is true. DF are collinear, then we know we can use Menelaus theorem on the triangle ABC and line DF. So we have that AF divided by FB times BD divided by CD or DC times CE divided by EA equals to 1. This is valid. So we want to know how can we relate this equation to this equation. We know that in this equation, there are all the ratio of segment. And in this equation, there are all the ratio of sine angles. So the sine angles in a triangle, how can we get a sine angle? When we calculate the area of a triangle, we use a sine angle, right? Let's say we have a triangle ABC. Then the area of ABC equals to half AB times AC times sine A, or half AB BC sine B, or half AC CB sine C. Right? When we calculate the area of a triangle, we need to use a sine angle. So that means we want to transfer the segment ratio to the area ratio. And then we can use this equation, transfer the area ratio that includes the sine angle ratio here, right? So AF divided by FB, AF divided by FB, AF divided by FB, equals to the area ratio of ADF, FDB, or the area ratio of AF, ACF, and FCB. So we know that here we want to include the sine angle ACF. So we want to translate it to the area ratio of triangle ACF, right? AF divided by FB equals to the area ratio of ACF divided by FCB. So ACF area, we can calculate it as a half AC times AF times sine angle ACF, and FCB we can calculate as a half FC. Oh, here it's AF times CF, FC times BC times sine FCB equals to AC divided by BC times sine ACF divided by sine angle FCB. Right, and for the next term, BD divided by CD, BD divided by DC, and we want to relate it to the angle BAD and DAC. That means BD divided by DC equals to the area ratio of BAD divided by the area ratio of CAD, right? Let me replace the pen. So the area of BAD equals to half BA times AD times sine angle BAD. No. Here sine BAD, here sine BAD, divided by half CAD, right? That's AD times AC times sine angles DAC. So this equals to BA divided by AC times sine BAD divided by sine DAC, and CE divided by EA equals to CE EA, and we want to relate to this angle, that's CBE, right? So CE divided by I mean the ratio of CE and EA is a ratio of area of triangle CBE and the area of triangle EBA. So that's equals to CBBE times sine CBE, and for the area of triangle ABE, that's half EB times AB times sine EBA, and this equals to CB divided by AB times sine CBE divided by sine angle EBA. Right, so if we multiply these three equations on the left side, that's AF divided by FB times BD divided by CD times CE divided by EA, that equals to 1. So 1 equals to here AC divided by BC times BA divided by AC times CB divided by AB times sine angle ACF divided by sine angle FCB times sine angle BAD divided by sine angle DAC times sine angle CBE divided by sine angle EBA, right? AC and AC, BA and AB are equal, CB and BC are equal, so this production is 1, and here, that means these three ratio, the production of these three ratio is 1. We prove the angle form of the Menelaus theorem, and now let's prove the converse of Menelaus theorem in angle form, right? So if this equation is valid, we want to prove that FED are collinear. And again, let's assume FED are not collinear, which means we can similarly as a proof procedure that we did in the converse of Menelaus theorem, right? We can extend the FE to a point D prime, and we can use that use the angle form of the Menelaus theorem on that on the triangle ABC and the line FED prime, right? That means we have this equation valid, and we also have 1 equals to sine BAD prime divided by sine D prime AC times sine angle CBE divided by sine angle EBA times sine angle let me see, BA, yes, sine angle ACF divided by sine angle FCB. Right, all other terms are the same, just this term. That means we have sine angle BAD divided by sine angle DAC equals to sine angle BAD prime divided by sine angle D prime AC. Right? So let's simplify this.